let's continue on now with a different subject related to solids, right? So up till now, we've been talking about the crystal structure of crystalline solids, but that's not the only important feature of solids. There is a separate kind of issue related to mechanical properties. And that characterizes a larger class of solid materials, crystals plus other non-crystalline solids, and distinguishes them all from liquids. Okay, so let's talk about that now. So for mechanical properties, and so a word for that would be elasticity. Okay, so the basic idea of elasticity is related to Hooke's law. Okay, so physics students typically learn Hooke's law in the context of a spring, right? And so let's suppose here we have a spring attached to a wall, and we pull on the spring. So there's some force, F, that's applied to the end of the spring. And because of that force, the spring stretches to become longer, like this. Right? So the original length is L, and it stretches to be longer, to be L plus some delta X. Under the influence of this force. And so Hooke's law says that delta X is related to the force by F equals K delta X. Okay, so this is probably familiar to most of you from basic physics classes. Now, of course, this is all true, not just for springs, but for blocks of material, right? So suppose you have some block of rubber, okay? So here, this is meant to be like a cylinder of rubber with an initial length L. And then if you apply a force, it stretches to be a little bit longer than it was originally under the force. And so it goes to some L plus delta X, like that. And again, there's a relation between the force and the extension. Right? The force is K times the extension. All right, so the first thing that I want to emphasize here is that the spring constant, K, doesn't just depend on the material, it depends on the size and shape of the block of material. So it depends on, I'll say, size, shape, and on the material. Now, we might want to separate out these effects, okay? So to separately talk about how does the spring constant depend on the size and shape versus how does it depend on the kind of material, whether we have rubber or iron or some other kind of solid. One way to do that is to think about different springs in parallel or in series. Okay, so if we have springs in parallel, So here's the wall, and here's one spring, and here's another spring, and you pull on both of them together, okay, with this force F. Then they both extend by some delta x. So there's this extra delta x, okay? And so for the first one, let's say these springs have spring constants K1 and K2. Okay? So they both extend by the same delta x because they're being held in parallel and stretched together. Okay. So for the first spring, there's a force F1 equals K1 times delta x. And for the second spring, it's F2 equals K2 times delta x. And the total force F is F1 plus F2. And so that's K1 delta x plus K2 delta x. So it's the combination of K1 plus K2 times delta x. Right? So this makes an effective spring constant for the pair of springs in parallel. Okay? So you could say that for springs in parallel, the spring constants add up. In general, if we were dealing with a block of material that's getting stretched, and then we compare that with a different block of material with a bigger area, right? So increasing the cross-sectional area of the material to some fatter bit of material like that, that's like putting springs in parallel, right? That all of the cross-sectional area is pulling together. All these forces add up and there's the same extension. So that tells us that the spring constant for the block of material is proportional to the area, where area is the cross-sectional area, perpendicular to the pulling force. Okay. Now, what about if we have springs in series? So if we have springs in series, let's see. So here's one spring with a spring constant K1, and here's another spring with a spring constant K2. So if we pull here with a force F, then the same force is transmitted everywhere along the line. So spring 2 pulls on spring 1 with the same force. Right? So spring 1 experiences that same force there. Right? And spring 1 therefore extends by delta x for spring 1 is that force divided by K1. And spring 2 extends so that delta x for spring 2 is the force over K2. Then there is a total extension, right? The total extension is the extension of spring 1 plus the extension of spring 2. So delta x total is delta x1 plus delta x2. So it's F divided by K1 plus F divided by K2. So it is 1 over K1 plus 1 over K2 times F. So this whole thing is a 1 over K effective for the springs in series. So this tells us that for springs in series, we don't add up the Ks, we add up the reciprocals of K. So this comparison of series versus parallel might be familiar to some of you if you studied electrical circuits, right? And so you can think about resistors in series or in parallel. So it's the opposite the way resistors are in series or in parallel. Okay, and the same kind of thing applies if you have a block of material. Okay, so if we have a block of material and we make it longer, right? So instead of the original length, we make it longer, then 1 over K is proportional to the length of the material, the total length of the material. So if you make the total length longer, 1 over K gets bigger. So K gets smaller. So K is proportional to 1 over L. So this then tells us how does the spring constant depend on the length of the material, this is 1 over length, and how does it depend on the area of the material? So we could combine those things, right? And say, if we combine them, that the spring constant for a particular block of material is the area, it's proportional to the area, it's proportional to 1 over the length, and then there's some constant of proportionality that doesn't depend on the area or the length. It depends on what the material is made of. So this thing, this constant of proportionality, this is called Young's modulus. We can work out the units of Young's modulus, okay? So we know, let's see, what are the units of K? All right, well, the units of K, well, let's go back to the original equation for Hooke's law. F is K times delta X, okay? So this is newtons, this is meters, okay? So the units of K are newtons per meter. Okay? And here the area is something in square meters, the length is in meters. So the units of Young's modulus are newtons per meter, so newtons per meter squared. Right? And this is pascals. PA is for pascals. Right? It's the units of pressure. And so Young's modulus is a property of a material. Okay, and so we could list some examples, right? And so if we have here a few things that I looked up, rubber is in the range of 0.01 to 0.1 gigapascals. And it would be aluminum is 70 gigapascals, and diamond is 1,000. So this is some indication of how easy or difficult it is to stretch a sample of rubber or aluminum or diamond. Um, all right, so this is a material property, right? And if you wanted to uh, predict the mechanical response of a block of one of these materials, right, you'd look up the Young's modulus for the material that you want and then multiply it by the area and length factors that correspond to the geometry of your sample. All right, so now let's take Hooke's law and rearrange things. Okay, so if we want to rearrange the factors in Hooke's law, we know that F is the spring constant K times delta X. So it is Young's modulus times the area over the length times delta X. So maybe we want to make an equation that just involves Young's modulus and not the area and the length. Okay. So one way we could do that would be to divide through by the area. Okay. And so we could say the force divided by the area is equal to Young's modulus times delta X over L. Right? And in that case, the thing on the right side is a sort of normalized force, right? It's the force normalized by the area over which the force is applied. And this is a sort of normalized extension. That is, it's the extension of the material normalized by the natural length of the material. So it's the percentage extension of the material, right? It's like saying a material is extending by 1% compared to its natural length. So there's a word for these concepts, right? The normalized force is called the stress. And the normalized extension is called the strain. Right? And so these are fundamental concepts in mechanical engineering, right? The stress being the force divided by the area, and the strain is the extension divided by the natural length. And for the units, you can see that the strain is meters divided by meters, right? And so it is dimensionless. And the stress is a force divided by an area. So it has units of newtons per square meter or pascals. All right, so this is a good way of thinking about extension experiments, right? What happens if you have some sample? So here's a sample that is a rectangular block of material, and if you pull on it this way, the force pulling on it like that, then it gets longer. And so the stress is the force divided by the area perpendicular to the force, right? So it's the area of the sides, left and right in this example. And the strain is the extension divided by the length, the natural length in the direction in which the material is stretching. Okay, so that is a simple way of characterizing this kind of stretching experiment. Now, there are other kinds of mechanical experiments also, because there are other ways to push on a block of material besides stretching it. Okay, so now let's think about a different kind of experiment, okay, called a shear. So for a shear experiment, suppose we have a sample that is initially a rectangular block, like this, and we apply a force sideways on the top. And correspondingly, we apply a force sideways on the bottom so that the net force is zero, right? If the net force were not zero, the material would just take off like a rocket, okay? But the net force is zero, right? Or perhaps the sample is mounted on a table and it can't slide with respect to the table. And so force, you apply a force on the top and the table provides the opposite force on the bottom. So in this kind of experiment, the material deforms. Okay, so it deforms so that the front surface is not going to be a rectangle anymore. It's going to be a parallelogram. And then that goes back and it's harder to draw. Well, something like this. Okay, so compared to its initial rectangular shape, you could say that the material, the top corner of the material, is moving by delta x, like that, okay, and delta x over here. And that delta x is proportional to the force that you apply. All right, but if you apply a small force, you get a small distortion. If you apply a big force, you get a big distortion. People characterize that, again, by a stress and strain. I think in the previous picture, I forgot to tell you two important letters for the stress and the strain, okay? The stress gets the Greek letter sigma, the strain gets the letter E, okay? So in this extension experiment, the stress is F over A and the strain E is delta X over L. That works in the shear experiment also, as long as we are careful to normalize by the right area and the right length. So here, the relevant length is the size of the system this way. Okay, so the distance between the opposite forces, right? If it's a bigger distance between the opposite forces, then the material can deform more. Okay, if it's a smaller distance, it deforms less. Okay, so the shear strain E is delta X over L, where L is this length of the system. Right? Then there is a shear stress. Which is the force divided by the area over which the force is applied. That means the area on the top and bottom, right? Because the force is applied all over this top area and all over the bottom area. So, whoops, wrong pen. A is over here, okay? So L is always perpendicular to A, right? A is the area over 2 dimensions, and L is the length in the 3rd direction in 3-dimensional space. Okay, and then these 2 quantities, the stress and the strain, are related to each other by the stress is a modulus times the strain, where this modulus is now called the shear modulus. So the shear modulus is a property of the material. It is a different property than Young's modulus. It is something else which is tabulated in books about properties of materials. And so some examples here that I looked up are rubber has a shear modulus of 0.001 gigapascals, and aluminum 30 gigapascals, and diamond 500.
Excuse me, is there a relation between shear modulus and the Young's modulus for the same material?
For the same material, yeah. That's an interesting question. These things, the shear modulus is less than Young's modulus, right? I mean, that's the first thing to say, right? It's less than Young's modulus because it is easier to deform a material in this shear way than it is to extend it. In general, for any isotropic material, there are 2 independent elastic moduli, and then you can calculate other parameters from those 2 things. Okay? So here I am telling you about 2 moduli. There are others. Okay? For example, another one is what if you apply a pressure from all directions, right? What if you put your block of material on the planet Jupiter, right? And so then the atmospheric pressure is pushing in all directions to reduce the volume, okay? So there's some other modulus that says how much does the volume change? For one more example, there is a quantity called a Poisson's ratio, which says if you stretch a material, it gets longer, but it also gets thinner in the direction perpendicular to the way that you're stretching. And so there's a ratio of how much does it get thinner compared to the amount that it gets longer. So those are 4 elastic properties of materials that I can think of. I'm sure there are more that mechanical engineers have thought of that I can't remember right now. For any particular material, there are 2 independent parameters, and the other things can be derived from those 2. For any isotropic material at a fixed temperature, say. So I'm giving you a quick summary of the first semester of a mechanical engineering class, and but all the other things can be derived from this in principle.
Okay.
So,
Vijaya, did you have a question also?
yeah. So,
okay. Okay,
so delta X, this displacement should be in the transverse direction all the time, or might be in longitudinal direction?
It's in the same direction as the force, right? And so in the shear experiment, because the force is this way, the displacement is also this way. Right? In the extension experiment, the force is extending things, and the delta x is also an extension like that.
Yeah, thank you.
Good, good.
I also had a question. It's just a quick one.
Sure.
Going back to your shear page where we're talking about shear stress. By the way the drawings are is the L for the second figure, for the figure on the right, is the L, is that the length before it was sheared? Is that the original? Like, is that the same distance as for the left figure? I'm just confused because of how it's drawn.
That's a great question, which I was hoping to gloss over, but you caught me. Ha ha ha. All of these considerations, right? These things are really rigorous, well, sort of rigorous, for the case of really small forces and small displacements. Okay. If you have a small force and a small displacement, okay, then what? Then the delta x is proportional to the sine of this angle theta, okay? The change in the length L is proportional to 1 minus cosine theta. Now, if you think about the Taylor series, right, 1 minus cosine theta, that's something of order theta squared, right? That's a smaller kind of quantity than theta itself, right? Sine theta is proportional to theta, right, which is linear in the displacement. But the shrinkage in this direction, that is quadratic in the force. And so that is it's not important in the limit of really tiny forces, okay? The distinction between this original length and this shrunken length. Okay. Now, I can say that, you know, as a physicist, considering that I'm not actually, you know, going out and building bridges or other things like that, right? Now, if you were taking a mechanical engineering course, then, you know, the mechanical engineers actually have to build stuff that can, you know, withstand big forces. And they really do have to think carefully about what are the relevant changes there. And that's part of the semester of mechanical engineering that I'm skipping over here, right? But it's a real thing, right? And so there are certainly books about that kind of effect. And so, yes, so it has to do, you know, in books you might see this described as finite strains versus infinitesimal strains, right? That what I'm doing is describing what happens for an infinitesimal strain, right? A really tiny little strain. But if somebody is considering a finite strain, that means, you know, what happens when there's a significant force and a significant change in the shape of the material. And engineers really have to think about that sort of thing. And there's a lot of work that's well established, and that's part of what engineering students need to learn.
Okay, thank you. So for our purposes, we're just going to say that L is basically the same for when it's sheared versus regular. Okay.
Correct. That will that will get you an A in this course, but that will not let you build a bridge. And so, you have to
All right, thank you.
consider more in some situations. Okay, Bajaya also?
Okay. So, in a solid, generally shear stress, shear modulus is constant, but in liquid, we can change the shear modulus by applying some external force. But in solid, we can't change. And could you tell us, is there any reason for that?
Well, okay. So here, I'm just getting into liquids. Okay, so thank you for that question. Now let's talk about liquids. Okay, so let's talk about liquids. All right, so let's suppose that we now try to do a shear experiment with a liquid. So, great. Shear on a liquid. So we have a liquid. So I don't know, here's maybe a rectangular swimming pool full of water. And we are, dragging across the top surface, right? So if we have, a big surfboard floating on the water, we pull everything across on the top. Okay? So we apply a force this way, and there is the opposite force on the bottom. Here we can see a big difference between solids and liquids, okay? Because in the solid, we get a strain, and then the material stops. Okay, that is, after a certain strain, a certain distortion, there's no more distortion, right, as a function of time. But by comparison, in a liquid, the material just keeps flowing. So if we pull across the top of the material, right, it induces some flow of the material. So the surfboard on the top is moving at some number of meters per second. And as long as you keep applying the force, the surfboard keeps moving at this number of meters per second. It doesn't stop. So it could keep going forever, right? Until you remove the force, right? So in a solid, you get a certain strain. In a solid, you get a strain, X, strain E. In a liquid, you get a strain rate. That is a strain per second. People write that as E dot. Okay? And so this symbol, it's an E with a dot over it. When you're speaking, you say E dot. Right? And the dot is an old-fashioned notation for a derivative with respect to time. Okay, so E dot, that means the derivative of E with respect to time, or you could say this is the derivative with respect to time of delta x over L. Right? Or you could say this is 1 over L, since this is approximately constant, right, times the time derivative of delta x. But this time derivative, this is the velocity of the top surface. Right? So this is a velocity divided by length. Right? So here, there's a big difference between the mechanical response of a solid compared with the mechanical response of a liquid. That is, with a solid, there's a certain strain and then it stops. Or you could say there's a certain delta X and then it stops, no more. Right? But with a liquid, there's a certain time derivative of delta X, so a certain velocity, and it doesn't stop. It just keeps on going and going and going as long as you apply the force. Now, there is a relationship in a liquid between what is the applied force and what is the resulting velocity. Okay? That relationship is that the shear stress is proportional to E dot. And the constant of proportionality is what's called the viscosity. Okay. So the viscosity, eta, is a material parameter associated with a liquid that tells us how rapidly does it flow in response to a shear stress. And so we can look up, well, first let's figure out what are the units of viscosity, right? Well, the shear stress on the left side, that is newtons per square meter. That is viscosity times the shear strain, which is, well, it's velocity over length, right? So it's meters per second divided by meters, right? So that's eta times 1 over seconds. Right? So the units of eta that is then pascals times seconds. So pascal seconds is the SI unit of viscosity. It doesn't have a nice name, okay? There is something related to it which has a nice name, which is called a poise. 1 poise equals 0.1 pascals per second. Okay? So you will often see tables where viscosity is listed in poise. Just be careful with that, because that is not an SI unit. And so if you plug it into an equation, you will get the wrong answer by a factor of 10 unless you are careful to convert things into SI. Oh, and just for a few examples of that, let's see. So water has a viscosity of 0.001 Pascal seconds at room temperature. And honey, for honey, it is 2 Pascal seconds, again, at room temperature. And so honey is way more viscous than water, right? Which you already know, right? You already know that if you apply a certain force on water, you get a really big velocity, right? But if you apply the same force to honey, it flows, but it flows much, 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 much more slowly, right? And so the viscosity is a way of quantifying that. Now, the point that I'm trying to get to is that the difference between the mechanical properties of solids versus liquids comes down to this distinction of elasticity versus viscosity. Right? That is, whether a shear stress generates a certain finite displacement, or does a shear stress generate a flow which keeps on going for as long as you're applying the shear stress. And this is the distinction that people are thinking of when they say you can hold a solid in your hands, right? So, you know, can you hold it in your hand? Okay, so suppose I want to see, right, can I put something on my hand, or will it fall between my fingers? Okay, so here, if I draw my fingers, this is like a cross-sectional view of fingers. Finger 1, finger 2, etc. All right, so I'm going to put something on top of my fingers like that. And then gravity is pulling down, okay? So gravity pulls down between the fingers, but then there's some normal force from the fingers that's pushing up on the material, okay? So you can see if you zoom in on the part of the material right here, this looks like the shear experiment on its side. And if you turn your head, it's the shear experiment, okay? Because there's a force this way and the force goes down over there. Okay? So it looks like there's a force applied over some area, which is the area of this surface or that surface, and it is changing over a length like that. Right? So that tells us then that the material will deform a little bit. So an exaggerated view would be that the material deforms a little like that, okay? And then it goes up over here. And then it goes down. Something like this, okay? And so if I have some very soft solid and I try to hold it, then it sinks down a little bit between my fingers and then it stops, right? And so it doesn't fall on the floor, right? It just sinks down a little bit, maybe only a very small amount, right? If it's a hard material, maybe the amount that it sinks down is so small you can't even see it. But in principle, it should be a little bit. By contrast, if we do the same experiment with a liquid, then you get a flow. Okay, so the material starts to flow and it keeps on flowing and it flows forever, right? And so if I want to determine is honey a solid, right? So I pour some honey on top of my fingers, right, then it will start to sort of slowly ooze down in between my fingers, and then it will fall down to the floor, right? And so there's no limit on the deformation, right? That honey just keeps going down, right? So this property of having a shear modulus versus no shear modulus, zero shear modulus, but just viscosity, that is a property of solids versus liquids, okay? So we could say that the solid has the shear modulus greater than zero, but the liquid has a shear modulus equal to zero and a viscosity that is something greater than zero. By the way, a very similar consideration comes when another way people describe solids is that people say a solid keeps its own shape, but a liquid conforms to the shape of its container. So, suppose we put some block of material, into a container, okay? So, here's a block of material. The material, at least initially, has a shape that's different from the container, okay? So there's a whole bunch of forces pushing on this block of material, right? It's pushing, I don't know, this way, and maybe there's a frictional force. There's lots of forces pushing in different directions, okay? And if it's a solid, then it stands up to these forces. And in response to these forces, it makes a little bit of a deformation, but only a finite deformation, and then it stops, okay? That's what we mean to say the solid keeps its own shape, right? By comparison, for a liquid, if you put it into a container and it doesn't initially have the same shape as the inside of the container, then it will start to flow. And it will keep on flowing until it gets the same shape as the container. And then there'll be no more net forces acting on it and it'll stop, okay? So this issue of the shear modulus equals zero versus shear modulus not equal to zero, this is the distinction that people have in mind with that kind of a description of solids versus liquids also. Okay, so let me just mention briefly a couple things and I'm going to stop. Okay, so as we've talked about already in this class, right? What I am presenting to you is the simplest version of the theory. And the name for the simplest version for the solid, people call it a Hookean solid because it follows Hooke's law, right? So it's named after that same Hooke, right? And for a liquid, people call it a Newtonian liquid. Because Isaac Newton figured out this stuff about viscosity, along with all the many other things he figured out. this is the simplest version of the theory. There are lots of extra complications that people put on. Right? So one kind of complication is what happens if there's a bigger force. Right? And so what kind of response is there that is not linear in the force? Okay? And so people make plots of stress versus strain. And for a simple Hookean solid, that should just be something linear. But for real materials, it might be more complicated. Maybe it's a curve of some sort, and people study that. That's an important mechanical engineering problem. Another kind of complication has to do with the time dependence, right? That is, what if you put on an oscillating force, okay? Some kind of AC force, and then you'll get an AC response. The response might depend on the frequency of the applied oscillation, okay? If any of you have studied electrical circuits, right, you know that when you have an AC electrical circuit, alternating current, right, then you can combine the concepts of resistance and capacitance and inductance into a complex impedance. Right? The same kind of thing works here with mechanical properties. And then the viscosity and elasticity get combined into something called viscoelasticity that has both of those together. And there is a shear modulus G of omega that depends on frequency, which is a lot like the impedance that depends on frequency in an AC circuit. It also is a complex number, the same way that impedance is a complex number for an AC electrical circuit. So, and then there are other complicated aspects about tensors, about relative directions of forces and displacements, which is, you know, a further sort of issue that people can study. But here I'm just trying to give you the basics that have to do with the distinction between solid and liquid. And that is something which I will continue on with on Monday, so that we can try to make a simple idea of how you can have a non-crystalline solid. So I will stop here. Please make sure to look at the homework that I just posted on Blackboard, which is due next Friday. I'll stick around and answer any questions. Thanks.